Its 36-year mission was to investigate unusual new realms, seek out anomalous cosmic rays and novel plasmas, and boldly venture where no probe has traveled before. Voyager 1 has been traversing outer space for over 4 decades now, and during that period, it has exceeded its original mission. The spacecraft was only anticipated to endure for 5 years, but it has defied all predictions. Now, it has taken a further step. Voyager 1 has just identified unknown entities passing through space, and this revelation has altered everything. The plasma originates from the explosion of massive stars millions of years ago, and that plasma carries the magnetic field of the galaxy with it. Join us as we unveil what these mysterious objects are and how they might transform our understanding of data forever. For the last few years, we primarily examined data from within the solar system, but thanks to Voyager 1, we now have access to information from beyond as well. In August 2012, Voyager 1 officially arrived at the end of the solar system and crossed the heliopause. However, this was not an easy feat as Voyager 1 moved further from the Sun. The amount of sunlight available to power its instruments and systems decreased significantly. The spacecraft's energy is mainly generated by 3 radioisotope thermoelectric generators, RTGs, that convert the heat produced by the natural decay of plutonium-238 into electricity. Over time, the diminishing heat output of the RTGs has resulted in a reduction in available power. This decline in power affects the functioning of various systems on board, including scientific instruments, data transmission, and communication capabilities. To conserve energy, certain non-essential systems and instruments have been turned off or placed in a dormant state. As the power continues to wane, critical systems may need to be further optimized or shut down to prolong Voyager 1's operational life. If it continues to function, it may not be as useful to us. The vast distance between Voyager 1 and Earth also poses a considerable challenge in maintaining effective communication. As the spacecraft ventured into interstellar space, the signal strength weakened substantially, and it now takes over 21 hours for signals to traverse from Voyager 1 to Earth. The weak signal, coupled with interference from background noise, presents a significant hurdle to successful data transmission and reception. In addition to power complications, there are temperature challenges. Transitioning from the heliosphere to interstellar space exposes Voyager 1 to different thermal conditions. Within the heliosphere, the spacecraft was closer to the Sun and experienced elevated temperatures. As it journeyed into interstellar space, it encountered extremely low temperatures, which can affect the spacecraft's materials, electronic components, and systems. Thermal stress and thermal expansion and contraction cycles might impact the structural integrity of certain parts. Severe cold can cause materials to become brittle, potentially leading to fractures or degradation of seals and connectors. These temperature fluctuations also affect the performance of the RTGs, which are designed to operate within specific thermal ranges. Cooling of the RTGs diminishes power output, exacerbating the power challenges. Interstellar space isn't completely void. It contains a sparse distribution of dust particles. Although these particles are tiny, they can pose a risk to Voyager 1. When the spacecraft encounters interstellar dust, the particles can collide with its exterior surfaces, causing wear and tear on protective coatings, antenna surfaces, or other sensitive areas. The accumulation of dust on the instrument's optics or sensors can interfere with their functionality, degrading data quality. Voyager 1 carries a dust detection instrument specifically designed to measure the density of interstellar dust. Additionally, the Deep Space Network, NASA's global array of antennas for communicating with deep space devices, must allocate limited resources to receive Voyager 1 signals, making communication opportunities less frequent than before. Amidst the influx of data, a fascinating revelation emerged. Voyager 1 detected an intriguing anomaly, a series of signals, most of which were difficult to decipher. However, one indicated the presence of 300 known objects passing through the cosmic expanse. These enigmatic entities, emerging from the depths of interstellar space, left scientists worldwide bewildered. The discovery of these 300 unidentified objects challenges our comprehension of the cosmos. Are they remnants of ancient celestial bodies drifting, relics from distant star systems, or do they signify the existence of previously unknown phenomena? uncharted realms waiting to be explored. Typically, when Voyager transmits information, it's relatively easy to interpret. But this data was jumbled. While many questions arose, there weren't really any answers. However, things took a stranger turn. Despite the peculiar nature of the transmitted data, Voyager 1 itself remains seemingly intact, functioning in remarkable condition. The great aspect was that its communication link with Earth remained stable, the signal maintaining its strength and allowing valuable information to be sent to NASA without much trouble. The investigation revealed that, curiously, none of the spacecraft's fault protection systems were activated, indicating that it hadn't even entered a protective safe mode, which would be the normal response if it detected any threats. So it was clear that Voyager wasn't truly under attack. But then, what could be causing the telemetry data to appear jumbled or inaccurate? Was it a result of interference from external cosmic phenomena, such as radiation or high-energy particles? Or was it conceivable that an entirely unknown phenomenon was at play? If the latter was the case, it would challenge our understanding of space and communication in the interstellar realm. The only way to ascertain the truth, though, was to meticulously analyze a wide array of potential factors. The research team at NASA carefully scrutinized the spacecraft systems, considering the impact of cosmic radiation on electronic components and the possibility of temperature fluctuations affecting the stability of its sensitive instruments. It was feasible that something was occurring just before Voyager hit the heliosphere, and the natural challenges in the way led to the scrambling of data. But the only issue was that it wasn't really in the area where the natural challenges were concentrated enough to pose a threat. The team also examined the complexities of Voyager 1's communication systems, investigating potential signal distortions caused by cosmic noise interference or even subtle shifts in its trajectory. The search for answers led the team to meticulously analyze potential factors. They thoroughly examined the spacecraft systems, considering the impact of cosmic radiation on electronic components and the possibility of temperature fluctuations affecting the stability of its sensitive instruments. While all of this sounds like a checklist, there's a lot that actually goes into it, and the research continued for weeks. The team employed advanced data processing techniques, developed innovative algorithms, and simulated various scenarios to isolate the root cause of the unusual telemetry anomalies. At that point, this was the only way they could determine what might be causing the issues. All that hard work didn't go to waste. After months of receiving jumbled data from the spacecraft, scientists and engineers ultimately restored the clarity and dependability of the information flowing in from the far reaches of interstellar space. The primary source of the problem was traced back to Voyager 1's attitude control and articulation system, ACS, specifically an unanticipated factor, an inactive onboard computer. You might wonder how something that isn't even meant to be operational could create issues. NASA officials disclosed that the ACS had somehow begun using a computer that had been dormant for years, resulting in the distortion of the transmitted data. However, the rest of the spacecraft remained functional and continued its data-gathering operations without disruption. Upon identifying the source of the problem, engineers quickly devised a remedy. They dispatched a command to Voyager 1, directing the ACS to switch to the correct computer for sending telemetry data. While this fix was relatively low risk, it required considerable patience due to the significant time lag caused by the vast distance between Earth and Voyager 1, with radio signals taking nearly 22 hours to make the round trip. The troubleshooting process necessitated extreme coordination. Yet there was one challenge. Given that Voyager 1 was constructed decades ago and had been operating flawlessly until this point, reaching the troubleshooting stage required them to sift through numerous manuals from the 70s. And they accomplished just that. After thorough investigation, they uncovered a straightforward and low-risk solution to the issue. By resetting the system responsible for data transmission, they managed to resolve the problem without interfering with any other components of the spacecraft. The engineers' expertise and commitment were vital in successfully restoring the clarity of Voyager 1's communication stream. Their endeavors highlighted the importance of utilizing past knowledge and merging it with modern technology to tackle challenges in space exploration. Engineers speculate that Voyager 1's shift to using the non-operational computer was triggered by a faulty command from another onboard system. This theory indicates an underlying problem within the spacecraft's complex computer network. Despite the concern, mission managers remain cautiously optimistic, stressing that the incident doesn't pose a serious threat to Voyager's long-term condition. In fact, Voyager surged past the heliopause issue and continued its mission right after the appropriate computers were reactivated. With that, it made history by successfully crossing the heliopause, the boundary that defines the outer limits of our solar system, where the sun's solar wind interacts with the interstellar medium. This marks the edge of the heliosphere, the region influenced by the sun's magnetic field and energetic particles. It is approximately 123 astronomical units from the sun, equivalent to an astonishing 11 billion miles. The heliopause lies at an immense distance from our star, to put it mildly. The heliopause is distinctive. Its shape is subject to changes influenced by the interstellar gas wind caused by the sun's movement through space. As the sun moves, it generates a magnetic bubble or foam within this boundary, shaping the heliosphere's outermost area. This magnetic foam contributes to the complex structure and behavior of the heliopause. When Voyager 1 and future spacecraft crossed the heliopause, several events occurred. First, there is a notable decline in the temperature of the solar wind-charged particles, which happens as the spacecraft moves beyond the influence of the sun's direct emissions. This alone is sufficient to render most spacecraft inoperable. But despite not being designed to travel that far, Voyager pressed forward anyway. Additionally, there was a shift in the orientation of the magnetic field, reflecting the changed influence of interstellar magnetic forces. Furthermore, there was a substantial increase in the presence of galactic cosmic rays, high-energy particles from distant cosmic sources that become more prominent beyond the heliopause but start to appear just before it. Voyager 1, being the first of the twin spacecraft to reach this remarkable milestone, offered humanity its initial glimpse into the uncharted regions beyond the heliopause, illuminating the enigmatic transition from the sun's light to deep space. In November 2018, Voyager 2 followed in its predecessor's footsteps, crossing the heliopause and entering interstellar space. This historic achievement marked a new chapter in our understanding of the boundary between the sun's realm and the interstellar medium. Voyager 2's encounter with the heliopause presented scientists with a unique opportunity to compare and contrast the observations made by both spacecraft, enhancing our comprehension of the celestial frontier. As Voyager 2 journeyed beyond the heliopause, it made intriguing discoveries that expanded our knowledge of this unexplored region. One significant observation was the sharp increase in the intensity of low-energy ions, a direct result of moving beyond the influence of the sun's direct emissions. Voyager 2 actually detected a simultaneous rise in the intensity of cosmic rays, high-energy particles originating from distant cosmic sources. Unlike Voyager 1, which experienced precursor events before its exit from the heliosphere, Voyager 2 encountered a different scenario. Instead of precursor events, Voyager 2 revealed the presence of a distinct boundary layer located just beyond the heliopause. In this boundary layer, low-energy particles streamed outward along the Milky Way, painting a fascinating picture of the complex dynamics occurring at the interface of our solar system and the interstellar medium as a whole. This unexpected finding highlighted the intricacies of the interstellar boundary and how it might not be easily predictable. If two spacecraft that appeared identical had entirely different experiences, it's challenging to ascertain how things would unfold for other spacecraft navigating the same area. Is NASA truly going to be willing to invest billions of dollars and gamble it all, knowing the potential for it all to be in vain? Well, as unbelievable as it may seem, despite the formidable nature of the heliosphere, NASA aims to learn everything possible about it and beyond. The Interstellar probe will be the one to collect all the data. The Interstellar probe is an ambitious NASA space probe concept that seeks to advance beyond what the Voyager spacecraft achieved. First proposed in 2018 by NASA's Applied Physics Laboratory, this groundbreaking mission envisions launching the probe between 2036 and 2041, embarking on a journey that will span several decades and cover hundreds of astronomical units away from Earth. At the heart of the Interstellar probe's mission is the necessity to gather comprehensive measurements and insights into the conditions prevailing throughout the heliosphere and the heliosheath. Yes, there's a distinction between the two. The heliosphere refers to the region influenced by the sun's solar wind, while the heliosheath represents the outer layer of the sun's bubble of charged particles. With the application of advanced contemporary technology, The interstellar probe signifies a substantial leap forward in interstellar exploration.